Before we finish the chapter and therefore the module, I want to talk about this secret section called 5.2 further vector calculus, which is optional. Okay, so if you are only interested in passing the exam and not in learning, you can leave, that's fine. I'm not going to include any of this in the exam. But if you are curious and want to know a bit more about vector calculus, so you know that we have this extra material, this optional chapter called 5.2 further vector calculus. Okay, so if you want to really know about it, I suggest you go into the PDF. So I provide the PDF in Kits, as you know, and you can open this 5.2 further vector calculus, which is clearly indicated as being optional. The contents on this chapter will not be on the exam. Okay, but I think it's really nice because it kind of justifies the things that you have learned in this chapter. For example, I provide the derivation of the divergence and the curl from their definition. So starting from the definition of the curl, I find, doing some calculations, I find the expression for the curl on, for example, this is along Z. And then you can repeat that same calculation to find the curl along X and the curl along Y. Then the derivation of the divergence from its definition. So it's starting from the definition, which is a limit. I do some calculations, calculate a flux of a differential volume, and I end up having the expression for the divergence in terms of the components and the coordinates. Then section B is about Stokes Theorem and the divergence theorem. I have to say these are one of my favorite theorems in all of mathematics. They are really, really, really nice. And I'm going to go like a briefly over them in this video, both of them. And then there is at the end of the chapter a section on the continuity equation, which I won't cover in this video, but it's also very, very useful and interesting. And you will see all of this next year. But I just think it's a shame, since you already know everything about flux, everything about multiple integration, about gradients, divergence, and curls. It's a shame not explaining this to you because it's so nice. So it's available there in the PDF. But in the meantime, I do have it like in some in the whiteboard. I do have like to make you like an overview of how these things look like. So let's start with the Stokes theorem. So imagine the Stokes theorem starts as follows. Imagine you have a field everywhere in let's say in two-dimensional space for now. Later we do it in 3D. And you calculate the circulation of the field around this path C1. And then you calculate the circulation around the path C2. So then you could realize that if you calculate the circulation around the path that includes both C1 and C2 like this green path here, the answer is going to be equal to the sum of the two circulations. Why is that? Because when you add up this circulation plus this circulation, this part cancels up with this one because they are going in opposite directions. So this leg of the journey in C1 is exactly equal to the leg of the journey in C2, but with a minus sign in the result of the integral. And therefore they will cancel out, and you will only end up with the remaining legs, which are the legs of C tot. Okay? And that can be generalized to any arbitrary shape like this one. You can always divide this area into smaller areas, calculate the circulation for each of those smaller areas, and the total circulation will be the sum of the individual circulations. Okay, and this is perfectly intuitive. So now let's move it onto 3 dimensions. You have a total path, which is this green path here called C total, and now I divide it into smaller paths like this, and this I call them C1, C2, C3, and so on. So now, of course, the total circulation is simply equal to the sum of those smaller circulations. So far, everything makes perfect sense, right? So now the trick with Stokes' theorem is to say, let's make this C1, C2, and C3 infinitely small. Okay? So once you do that, it turns out that each of these small squares is just a differential of surface, which has a contour, which is a differential of the contour. Okay? So you can literally write that now the sum becomes an integral, becomes a surface integral, because you are adding up all of the differential circulations on each of the ds's, right? So you have to do the double surface integral of dc, which is the differential of circulation. But now, since the curl is defined as the limit of the circulation divided by the surface, when the surface goes to very small, you can write it as this fraction of the differential circulation divided by the differential surface. And if you substitute that here, so dc is equal to the curl times ds, so you can find that the total circulation around the total path is simply equal to the surface integral of the flux of the curl. Okay, that's amazing. So basically you are relating the circulation along a path on the outside, you are relating it with adding up the curl, the flux of the curl throughout the entire surface. So you are relating the surface with the contour. And this is very much related to Ampere's law, which says that the total circulation of the magnetic field is equal to the current that crosses this surface. That's because the current, according to Maxwell's equations, the curl of the magnetic field is equal to the current. So that's why you have to add up all of the currents that crosses the surface to find the circulation. Okay, so really amazing. The divergence theorem, also known as Gauss's theorem or Strogatsky's theorem, is actually very, very similar. Imagine you start with two cubes and you calculate the flux flowing out from these cubes. And now you create a bigger cube that encompasses both cubes. So it turns out that the total flux of the big cube is equal to the sum of the fluxes of the two small cubes. And that's because the component of the flux for the cube 1 cancels out exactly in those faces that are shared by the two cubes. So they cancel out. So the only faces that end up counting when you add them up are the outside faces. So all of the outside faces, which is the flux of the total volume. And you can do this arbitrarily. You can always divide a volume into tiny cubes, yeah, and calculate the flux for each of the cubes. And they will always have some sides which are shared, such as between 7 and 9, you have these sides which are shared. And they will always cancel out when you add up the fluxes for each of the individual cubes. So that the total flux, when you add them up, will be the flux outside of the big volume, which is marked in green here. Okay? So this is what I write here. So now we do a very similar thing. We take this to the limit in which the small cubes become a differential of volume. Okay? So we divide a certain volume into differentials of volumes, these mini cubes, and we calculate the flux for each differential of volume, and we add them up, and we know that the result will be the total flux for the total surface that encloses all these volumes. Okay? And now, by using the definition that the divergence is simply the flux out of a differential volume divided by the differential of volume, we can substitute that into this statement that is saying that the total flux on the total volume is simply equal to the volume integral of the differentials of the flux for each of the dVs. So we substitute d phi here, and this becomes the divergence of F multiplied by dV. So you have now turned the flux integral on the surface is equal to the triple integral on the volume of the divergence of F. And this is Gauss's law, which you have used to calculate the electric field of a charge, because the flux of the electric field on the outer surface is equal to the total charge inside of the volume. Yeah, and that's Gauss's law. Really, really elegant. So I hope you enjoy this, and I now hope that you go to the actual PDF in which things are explained much more properly. They are not as hand-wavy as I just did it, but they are properly explained. Okay? Excellent. Thank you very much for watching, and I hope you enjoyed the chapter and also the entire module. Thanks.